All right. So we left off chapter 17. We had talked about reactivity, we had talked about naming, and we talked about the general reaction mechanism for a nucleophilic acyl substitution. And we also talked about what reagent you need to form an acid halide from a carboxylic acid. And then we just did a bunch of examples here. And so today we're going to start out with lactones and lactams. So those are really fun. A lactone is a cyclic ketone. I'm so dumb. Oh my God, sorry. It's a cyclic ester. And a lactam is a cyclic amide. So the way I remember this is lactam is an amide. Lactone has an O in it. So it's an ester. So once you know which one is a lactone and which one is a lactam, we have to go in and kind of number this. So if anyone remembers from chapter 16, we have the carbonyl carbon. What is this carbon next door called? Alpha, yes. And do we want to take a guess on what this one might be called? Beta. Any guess what comes after that? It's like an upside down fishy. Gamma. And then last but not least, we have delta. So alpha, beta, gamma, delta. And we're going to name this with the highest letter. So this guy is a delta, that doesn't look like a delta, lactone. Next up, yes.
Rose, did you pick that just because that one's closest to the O?
So you could think about it like that, but we could also say like we're gonna use like the highest number usually in chemistry, right? But instead of numbers, we're going to do letters. So the way we know it's like a bigger chain, sorry, that's a weird way to explain it. You can think of it as it's the one next to the oxygen, or you can say like it just signifies the bigger ring when we use the higher letter. And I will write it down because someone asked. This is the delta. So I'm going to point to a carbon and you please tell me what it's called. This one. Alpha. This one. Beta. This one. Gamma. Exactly. So this is going to be called a gamma lactone. And I guess a better answer to the question that someone asked me just now, or like a minute ago, when we get smaller, we like subtract from this side. So it wouldn't make sense if we called this one alpha and then this one beta and then this one gamma because then it like we lose carbons as we go on. So you kind of have to think about it as going the other direction, if that makes sense. Okay, so this carbon, what do we call that? Alpha. Next one. Beta. And someone said, I just think of it as starting from the carbonyl. That's how I like to think about it too. But I just wanted to give a couple different ways for people who maybe didn't see it, you know. So this is a beta lactone. And next we have an alpha lactone. So I will zoom out so you can see all of those. All right, now we have to figure out how to name our lactams. And we can assume that since it's a nitrogen instead of an oxygen, everything is going to be different, right? No, not at all. So it's actually going to be named exactly the same. Alpha, beta, gamma, delta. We love to see it. Yes, we do. So this one again is a delta lactam. And so what's this guy called? A gamma lactam. Our square friend. A beta lactam. And last but not least, we have our alpha lactam. Ta-da! So I shall give you a moment with the lovely lactones and lactams. And then we're going to do the really fun stuff and we're going to make and break these suckers. And for that, I'm actually going to open up a new, I wonder if I have that in the handout. Nope, of course I don't. Nope. Okay, so I will be making a new page. Sorry about that. So first we are going to make make lactone. And whatever I do for the lactone, the same exact thing happens for the lactam. Just replace the oxygen with a nitrogen. And that'll make more sense once I actually start drawing things, but I wanted to put that disclaimer out there. So, let's say I give you I'm gonna actually change this pen because it's driving me crazy. Ballpoint. Okay, that's better. Sorry about that. So let's say I give you bam, 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 bam. What functional groups do we have here? We have an alcohol and acyl chloride. So on a scale of benzene to, sorry, that was going to be such a dumb joke. I was going to say from benzene to cyclopentane or cyclopropane, how stable is this guy? Um, that was a dumb chemistry joke. Is this really stable or is it really unstable? Everyone's like, yeah. We're just gonna leave that. Yes, this is extremely unstable. If you guys remember from the order of reactivity that we looked at, acyl chlorides are really, 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 really reactive. Super reactive. So we want something to attack it, right? And luckily, I'm gonna give you reagents. So I'm giving you NaH. What do we do with that? That doesn't look to be any set of reagents. IDK Rose, what do we do? That was really, really funny. Okay, so we know that Na is a plus, so we know that H has to be minus, right? And so we've seen H minus in the semester before, and that was in reduction reactions. But in this case, we can actually have two options. So either it can act like a base and steal that hydrogen, or it can act like a nucleophile and directly attack the carbonyl. Which one do you guys think is favorable? Base or nucleophile? Okay, we got one vote for nucleophile. We also got one vote from the same person for base. Okay, we got some more base. Okay, cool. So I agree. The reason we choose base instead of nucleophile in this case is because it is so much work to go over here, attack, start a reaction, blah, blah, blah. That is so much work. Instead, this guy could just come here, snatch this easy to take acidic hydrogen, and we can be happy, happy campers. And yes, we did do an example very, very, very similar to this last session. I was implanting an idea into your brain, and now we're talking about lactones, so I have to do it again. But yes, we did. Look at y'all paying attention. Okay, so we're gonna erase this ugly nucleophile path because we know that doesn't happen. And we're going to leave the base path. So yay, hydrogen acts like a base and it steals the other hydrogen. So at this point, these electrons go back to our oxygen. And all we've done is bam, 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 bam. And what charge is left on the oxygen? So, okay, you guys said negative here, but someone also had a good question, which was, is it always going to go the base path, or is there going to be two options and you have to choose every time? So, in this type of reaction, it's always going to be a base because that's more favorable. So, if you have an acidic hydrogen, the negative charge will always be a base. Thank God. Yeah. 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 We were just doing it one time just so you guys know the concept. We're not going to do that anymore. Just base is the law for now. All right. So at this point, we have something with a negative charge and we have a carbonyl. Hey, this looks really familiar. This looks like one of those reactions where we pick a leaving group, we pick our nucleophile, and we don't even have a hydrogen to get rid of. I dropped something. Ignore that. So we're going to do a nucleophilic acyl substitution. This is going to come here, and we're going to kick off the leaving group. And yes, I'm shortening the mechanism a little bit, but that's okay. Now, my favorite part of the reaction, counting. So 1, 2, 3, 4, and the oxygen is going to be inside the ring, so I am going to number it 5. So now we have a 5-membered ring. Let's draw that out. This is the new bond that we made. Carbonyl. So we have carbon 1, 2, 3, 4, and oxygen is number 5. And on carbon 4, we have a methyl. And someone asked, why do we give the oxygen a number? So the reason I like to number it is because in this example, this oxygen is attacking here, so it goes inside the ring. It's part of the ring. Whereas in other reactions we've done before, it ends up outside. And so I just want you guys to differentiate. Like this one goes inside, so it has to be a 5-membered ring, not a 4-membered ring. Ah, someone said a glitch. Okay, so I'll just say that one more time. So the reason I gave number 5 a number, or oxygen a number, is because a lot of students will number 1, 2, 3, 4 carbons and make this a 4-membered ring. But remember, oxygen is part of the ring. It's inside. So it's actually a 5-membered ring. So to avoid any confusion, I give the oxygen a 5 just so you know it's in the ring. Ta-da! Okay, so what do we name this guy? And I can guarantee it's probably simpler than what you're thinking. It's a lactone, yes, but a little bit more specific. Ooh, okay, someone said 4-methyl-lactone. A little bit too specific. Find something in the middle of those two answers. Hint, it has to do. Someone said, I know I'm correct because you got too excited. That's hilarious. So technically, yes, this is a 4-methyl gamma lactone, but for the purposes of this class, as long as you know that it is a alpha, beta, gamma lactone, you are good to go. Ta-da! That's why I said it's simpler than you're probably thinking, because you don't actually have to name the substituent. That's only for this class. He's not going to ask you specifically, like, oh, name the IUPAC name for this lactone. As long as you know it's a gamma or an alpha or a delta or a beta, you're fine. But in the real world of chemistry, yes, this would be a 4-methyl gamma lactone. So you can do this. Someone asked me to scroll up, so if you want me to go up to the other page, let me know, but I'm going to give this a moment in case people need it. Yes, other page. Okay. Bum, ba-dum, ba-dum. Yeah, I'll just zoom in. Sorry. You're very welcome. Okay. So now we're going to do something almost even more fun, if you can even imagine that. We're going to break lactones. So now we're going to essentially do this reaction in reverse. So let me give you what kind of lactone is this? Well, now it's a nothing lactone, but delta. So we have our delta lactone. Cool. And so for breaking lactones, we can really use any nucleophile and any catalyst. So I'll just make a note of that. Any nucleophile from chapter 17 and acid/base will work. So for funsies, let's give this HCl, and to spice it up, let's give you NH2. When we have an acid catalyst, how does that affect the reaction? It makes the electrophile more electrophilic. Hell yeah. Okay, so as we've done approximately 1,700 times this semester, we're going to use these lone pairs. We're going to attack. We're going to steal a hydrogen. And we get a plus charge. Bam. So now our nucleophile comes in. And please remind me, what is our nucleophile? Please be as specific as possible. Nitrogen. Yes. So let's highlight that. This is our nucleophile. And what is our electrophile? Be as specific as possible, please. So the lactone, the carbonyl, both are correct. The carbonyl carbon, yes. So this right here, electrophile. And, when we see that we have a carbonyl and a nucleophile, we know that this is either a chapter 16 or a chapter 17 question. How do we tell the difference between chapter 16 and chapter 17? Sounds like, I don't know. Kidding. Someone said the type of electrophile. Could you be more specific? You're on the right track. Yes. Okay, cool. So in chapter 16, we had ketones and aldehydes. In chapter 17, we have these new things, carboxylic acids, amides, acid halides, and those are all in a group called the carboxylic acid derivatives. So we know that a chapter 17 question, we can do easy peasy lemon squeezy. We find the leaving group. We already found the nucleophile. And we get rid of a hydrogen. So the tricky part here is it's in a ring. So first things first. 1, 2, 3, 4, 5. And someone said, what's the leaving group? Precisely. So remember, when something is a leaving group, it has to have a carbon oxygen bond, a carbon nitrogen bond, a carbon sulfur bond. It has to be something that's not carbon-carbon or carbon-hydrogen. Another way we can say that is it has to be a bond between a carbon and a heteroatom. So this bond right here is the one that's going to be broken. And so the thing I highlighted in yellow is the leaving group. And so yes, this is a nucleophilic acyl substitution reaction, correct. So how I like to do this is we start with a carbonyl because I said so. Plus carbon 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Off of carbon 5, since we broke this bond that way, we have an O attached, an O minus. And on the other side, on carbon 1, is where we attached the nucleophile. So we get this. We have a plus and a minus on the same chain. So Wait, before we do that, someone said they are confused. So, yes, the oxygen is a leaving group, right? But it's connected to the chain here and here. So if you only break this bond, this oxygen isn't just, it's not going to just go away. This is going to break open and the oxygen is left on carbon 5. So it's a leaving group because it detaches from the carbonyl carbon, but it hangs on the other side. Exactly, exactly. So I'll even highlight that. This was our leaving group. This was our nucleophile. And we learned something handy dandy in chapter 16 that involved moving one hydrogen from one place on a molecule to another. What do we call that? I know that was kind of a weird explanation for it, but I didn't want to give away the name. Not a hydride shift, not exactly. I'm saying like, what's it called if this oxygen were to steal a hydrogen from this OH plus? Intramolecular something or another. Good enough for me. So we're going to call this an intramolecular proton transfer. Heck yeah. So it's going to pain me that I can't just copy and paste this, but that's fine. That's so ugly. I'm so sorry. So we end up with an OH, and we end up with an NH and the R group. And yes, I can draw the arrows for the transfer, my bad. Someone said I actually can copy and paste, so I will try to figure out how to do that because I couldn't do it earlier. And someone said something, but it disappeared. Okay, so someone said they thought the intramolecular proton transfer was when it attacked itself. So an intramolecular reaction is when something reacts with itself. And specifically, the intramolecular proton transfer is when one atom on the molecule takes a hydrogen from another atom. So we go from a plus and a minus to neutral. Hold on. Let's see this magic. Copy. It won't paste. Am I just being...
Like, okay, press the pen.
Okay, pen.
Press the pen on the screen and hold it there. No, no.
Okay.
Go to the last
Oh,
one.
okay. Okay.
Hold it. No, you don't have to circle. Just press the
Oh,
pen and
okay. Oh, that's
paste.
beautiful. Thank you so much. I promise I'm not like 87 years old. I'm hip. I'm young. I can use the technology. This is just getting worse by the minute. Um, okay, so this is making and breaking lactones. Any questions, comments, concerns, strange inquiries? Okay, so let's go back up here and let's do this problem. So, gamma lactone, how many membered ring is that for a gamma lactone? Ooh. Okay, so someone said a 5-membered ring. Let's see how that checks out. We got alpha, beta, gamma. Perfect. And yes, I can go back right quick. Ta-da. Stop it. Stop it. Stop it. Oh my goodness. There we go. Crisis averted. Okay, cool. So let me just fix this because it's driving me crazy. All right, so we are trying to make this thing, right? So in order to form this, we need to have some carbon chain that has a carbonyl with a leaving group. And in order to make it gamma, we have to go 1, 2, 3 carbons away, and we have to end up with an OH here. And so you can think of that as alpha, beta, gamma. On that gamma position, you need an OH. So let's look for an answer that has that. So I'm going to zoom in a tad to each answer choice. So we find the carbonyl carbon. Oh, yes, I can say that again. Okay. So we want to form this, right? And we know that because it says which will form a gamma lactone. And a shortcut to figure out how to form a gamma lactone is to just think backwards, right? So when we did this reaction here, we know that in order to form a lactone, you have to have a carbonyl with a leaving group and an OH on the same molecule. So you have to find the answer choice that has an OH and a carbonyl with a leaving group. And in addition, you have to have the OH a specific number of carbons away from the carbonyl. And yes, I am recording. So for a gamma lactone specifically, you can go in, start at the carbonyl carbon. This is alpha, beta, gamma. On that gamma position, you have to have an OH. So that when you react, this will eventually attack here, and you will get a 1, 2, 3, 4, 5-membered ring. Ta-da. Let me know if that was too fast, or if you kind of understand what I mean by that. Okay, so someone said not really clicking, and someone said they kind of get it. So let's... Okay, I'm going to try to think of another way to explain it. Let's try to start here, right? We know that... Actually, let's start here. We know that in order to form a lactone, we have to start with an OH and a carbonyl, right? Because we have that attack, we form a ring. And to get a gamma lactone, we started with an OH that was over here. If we started with an OH that was here, it would attack and form a 1, 2, 3-membered ring. So, if he asks you a question like this, where he says, which will form a something lactone, I want you to draw out that type of lactone. In this case, it was a gamma again. And we're going to work backwards to find how far away the OH has to be in order to form a 5-membered ring. And the way we do that is we start at the carbonyl and we're going to number backwards. So the carbonyl carbon is number 1, 2, 3, 4, 5. Or the easier way to do it, in my opinion, is alpha is the carbon next to the carbonyl, then beta, then gamma. And in order to form a gamma lactone, you have to have an OH on the gamma position. And so when we go to the answer choices, what we're going to do is identify the carbonyl carbon. And we know this because Rosemary told you to memorize a couple of those condensed formulas. So CO2CH3 looks like this. So we have our carbonyl carbon, and we can say this is alpha, this is beta, this is gamma. That looks pretty good so far. Let's try this next one. This is the carbonyl carbon because COCl looks like this. So starting from there, we have alpha, beta, gamma, delta. That's not a delta. Delta. So this reagent would make a delta lactone. We don't want that. Answer choice C. We have so much going on here. This is meant to confuse you. This CO2 looks like this. And then we have a carbon like this. That's really ugly. The purpose was just to make it confusing so that you might pick this carbon as the carbonyl instead. But it is this one. You won't get that on the exam. I just wanted to be mean. So this is the carbonyl. We say alpha, beta. Beta carbonyl equals a beta lactone. We don't want that. Last but not least, this is a carbonyl carbon. We have a carboxylic acid. So this is our alpha position. And so this would make an alpha lactone. So which of these answer choices make sense? A, perfect. I agree. So I will zoom out. I'll give you a moment to soak that in. Any questions? Questions, comments, concerns? Can we call it a day? Can we call it a day? Yes, we are calling it a day. We're technically done. We went a minute over time. I'm so sorry. I wanted today to be kind of a more chill day, so I hope I didn't hurt your brain too much. But you guys did amazing. I am so proud of you for getting through that exam. You did wonderful. The semester's almost over. We got this. So close. 3 exams done, 1 left. Yay! No, but I'll have to stalk your YouTube. That's what it's there for. And okay, I make no promises because every time I do, I don't end up doing the thing I promised. But this weekend, I am going to hopefully go through all the YouTube videos from this semester and put something in the description so it says like what chapter we're talking about or what topics we're talking about so that it's easier for you to navigate when you study for the final, because I realize it's not cute. And and someone showed me how to do like little like I don't even know how to explain it. Like little ticks in the video so you know like where chapter 17 ends and where chapter 18 starts. So I will attempt to do that for you as well. I am a grandma, so we'll see how that goes. But yes, I'm going to stop talking and I'm going to let you guys go. Have a wonderful day. I will stick around if anyone has questions, but that's all I got.